welcome to the concepts video on exponential functions. So I'm going to start off this section by talking about linear functions. We're going to do kind of like a blast to the past, not so far ago, right? But we have linear functions, and let's look at the general form of them. So linear functions usually looked of the form like f of x is equal to, let's say, here's an example, 2x plus 3, right? And the defining feature of linear functions is that it has a constant rate of change, right? And the rate of change, which I'll abbreviate ROC, the rate of change is, or was, well, for a linear function, it is a constant number, right? So what do I mean by constant number? It just means when x increases by 1, so when you bump this guy up 1, then your y value, or your f value, the function value goes up by 2 each time, right? So if you plug in a 1, then you get out 5. If you plug in a 2, you get out 7, and each time your function value goes up by 2, or by your rate of change, right? But now, we're going to look at exponential functions. So exponential functions. Okay, so with exponential functions, the defining feature of these is that our rate of change, so our rate of change is now not a constant numerical change, but now a percent, or also denoted as percent, change. Okay, and I'll show you what I mean by this. All right, so for exponential growth or decay, because there are two different kinds, but both of them are exponential functions, our general form for our function is going to be f of x is equal to a, which is a constant, times 1 plus r, and then raised to the x power, okay? So let's break down some of these variables. What's going on here? So a is our, let me actually do this on the next slide where I have some more room, okay? So here's four exponential functions, and they look of this form right here. Okay, so what is a? A, that, like I said, that's a constant, which is, it represents your initial or starting value of your function, okay? Starting value, okay? So this is basically when x is equal to 0. So this also tells you your vertical intercept, right? Like your y-intercept, or f-intercept in this case, okay? All right, let's see what else do we have. So let me just write a little note. On your graph, this is your vertical intercept, okay? So you'd have the point 0, comma a, alrighty? And then let's look at another variable. We have r. That one's super important. This one is going to be your percent growth or decay rate, okay? And I'll show you like what determines whether our exponential is a growth one or a decay one, okay? We'll go into that in more detail later on. So this just means the percent rate that you're looking at, okay? And what's really important about this is that we write r, like let's say you have 14%, then you would write it as 0.14, okay, or 0.14. So this is written as a decimal. Written as a decimal, okay? That's an important part. Written as a decimal. Okay, let's look at another thing. Oh, one thing I do want to mention, well, x is commonly, x or t, sometimes you'll see, x represents time usually, okay? Time, usually. Like time that has passed since a certain point, okay? Alrighty, and one other thing that I would like to mention is that you could also see a form where we have f of x is equal to a times b to the x, where b is just replacing our 1 plus r, okay? And in this sense, b is called our growth factor, okay? Let me just write that in here. This is just an alternative way to write it, where b is equal to 1 plus r, and b is sometimes considered your growth factor, okay? So that way you don't have so many terms floating around, and we can kind of just consolidate it into this nice compact form. Okay, so here's an example of a problem we could get. So let's say John has $100 right now. His grandpa decides to give him 50% of his total at the end of each year that passes from today. What is his total after 2 years from today? Okay, So first of all, his grandpa is very generous. And then now let's see, okay, so we can tell that this is going to be an exponential kind of function. We can model this situation with an exponential because we have a percentage increase, a percentage rate of change, okay? It doesn't say his grandpa's going to give him $50 per year for the next 2 years or whatever. If that were the case, then we would have a linear function, right? Because we're dealing with actual numerical values, like $50. That's just a fixed numerical value, right? But here we have 50% of whatever he has, of whatever John's total is, right, at the end of each year. So in this case, because we have a percent rate of change, the amount that is being added each time or each year, it depends on what his total is at the current year, right? So anyways, let's see, we're going to whip out our the general form of an exponential function, right? And then we're going to see, okay, what variables can we identify? So A is our initial amount, right? And so in the beginning of the problem, it says John has $100. So A is simply going to be 100, okay? And then as we move along, it says Grandpa decides to give him 50%, right? This is our percent rate of change. So that means R is going to be not 50%, right? Because we want to write it as a decimal. So this is going to be 0.50, right? And because his grandpa's going to give him this much, that means he's adding to his total. So the rate of change, or the percent rate of change, is going to be positive, okay? So we have this plus 0.50, okay? And then what is his total after 2 years? So then after 2 years, if we measure x in years, that means our x is going to be 2, okay? So if we plug this all in, let's just write our general formula first. So f of x is equal to 100. That goes in for the a spot, right? And then we have 1 plus whatever r is, and that's a 0.50. And then we just have our x up there. Okay, so this is our general function, or formula for our function. Okay, and now we want to plug in this x equals 2, because that's what the question's asking. What's his total after 2 years? And this gives us the total. So we're just going to plug in f of 2 is equal to 100 times 1 plus 0.50 to the 2 power, or to the squared, we could say. Alrighty, so this is basically just going to give us 100 times 1.5 squared, which turns out to be 100 times 2.25. Okay, so we get 225 as our total. So this is he's gonna have $225 after 2 years from today. Okay, and I just want to show you guys another way to think about it, and like what is this power doing up here? We could say, going from this step right here, we could write this as 100 times 1 plus 0.50 times another one. We could just expand it out, right? This is the same thing as saying this whole quantity thing squared. It's just that times itself, right? So we could say, okay, so this one right here that I'm grouping, that's after 1 year, right? That's what he's going to get. That's what his total is going to be. And then we apply this guy again. We apply the percent rate of change, okay? So the exponent basically tells you how many times we are applying the percent rate of change. Percent rate of change. How many times we're changing the total, okay? Alrighty, here's a very similar problem, right? We still have John, and he's still starting with $100, and this time it says his mom is going to withdraw, so take away, half of his total amount at the end of each year to put in a savings account. So what is his total after 2 years? Okay, so there's an important difference that we have to clarify here, is that on the previous problem, we had that R was equal to plus, or a positive, 0.50, right? Because his grandpa was going to add 50% of whatever he had to his total. So he was going to add that much. But now we're looking at, so now with this problem, we have that his mom's going to withdraw half of his total at the end of each year. So half still means 50%, right? So we have this 0.50, but because we're withdrawing, so we're taking away from that total, we have a negative sign in front, okay? So this is the problem we're working on now, okay? So again, he starts with $100, so again, A is 100. This time R is negative 0.5, or 0.50, right? And then again, X is going to be our 2 years, right? So if we formulate our function here, we have 100 times 1 plus R, so this will be 1 plus a negative, so that's like 1 minus 0.50, and then raised to the x power. And now let's just plug in our 2, right? So we get f of 2 is equal to 100 times 0.5, and then to the, or squared, right? So then we just get that this is going to be 100 times 0.25, and we just get a $25 out, okay? So now we just get $25. That was pretty simple, and I mean, you could always check it. Well, you not always check it, but sometimes with simple examples like these, we can check logically to see if this makes sense. So he started with 100. This is now, right? And then after 1 year passes, then his mom's going to take out half, right? So then he'll have 50, and another year passes, another year, okay? And then we're at 25, right? And that's where he ends up. That's where his total is after 2 years, okay? Alrighty, so let me just do a quick comparison between the two examples that we've just witnessed. So we had, I'll just write grandpa example and the mom example. Okay, so what is the difference between these two cases? I kind of alluded to them already, but here we had, okay, so his grandpa was going to add 50%, so he was going to increase his amount, or increase his total by 50% each year. Right? So a 50% increase. So that meant that our R was equal to positive 0.50. Okay? Whereas his mom was going to withdraw 50% per year. So that would have been decreasing his total. So that would give us this negative, R is equal to negative 0.50. Okay? So that's basically the crux of the whole difference between these two problems, is just the percent rate of change, right? Just the negative sign versus the positive sign. And building off of that, we can say that the growth rate, or the growth rate, which is denoted by B, which is equal to 1 plus R, for our other example, or the other form, you know, A times B to the X, right, as opposed to A times 1 plus R to the X. So our B in this case would be 1 plus 0.5, so we get 1.5 out of that. And our B in this case is going to be 1 plus R, so that's 1 minus 0.5. So this would give us 0.5, okay? And let's see, what else do we have here? So, and as we saw, when in the grandpa case, where we had grandpa adding 50% to John's total each year, we had the amount increases exponentially, right? So increases exponentially, okay? And so this is a case of exponential, and I'll just abbreviate, exponential growth, okay? Exponential growth. So if we were to graph it, this is what it would look like. Something like this, okay? So we're growing as x goes along. So as x goes along to infinity, as it moves to the right, then we have that the function value is also going to infinity, okay? Alrighty, and this happens when, as we saw, when our R is positive, okay? So when our percent rate of change is going to be positive when it's growing, right? And then our B is greater than 1, okay? Alrighty, so let's explore some more on the other side. So here we had that because John's mom was withdrawing 50% each year, the amount was decreasing exponentially. Decreases exponentially. Okay, so this is going to be a case of exponential decay. Alrighty, and that is characterized by our percent rate of change being less than 0. Okay, so when it's negative, like this one here, and so that makes our B become less than 1 because you subtract R from 1, right? So anyways, this graph is going to look like the following. It'll also be positive, but this time it's just going down instead of up, right? So here we have exponential decay going on. So as x moves to the right to infinity, as x goes this way, our graph is not going to negative infinity, but instead our graph is approaching 0. Okay?